Alright, so today we're going to look at our final lesson on factoring, and it is in fact on factoring binomials. And we've kind of been factoring binomials here and there with factoring out a GCF, but today we're going to look at a special type of binomial called a difference of squares. So a difference of squares can be identified because you have a perfect square minus another perfect square. So the steps are still kind of similar. You're still always checking for a GCF first, and then if you notice that pattern that you have a perfect square minus another perfect square, then you can set up your binomials. A difference of squares is the only type of binomial that factors into two more binomials. So let's go ahead and take a look. So here I'm seeing I have 25x squared minus 64. So I have that perfect square minus another perfect square. So I'm going to set up my binomials. And if I take a look, 25x squared is created by multiplying 5x times 5x. That's how you get both of those terms to be a perfect square. And then if we look at 64, well, the two terms are the same term that multiplies by itself to give us 64 is 8. So now we have to consider, well, what's going on with the signs here that are causing the middle term to cancel, right? Because if the middle terms didn't cancel, we would have a different type of trinomial, right? So here, one must be positive and the other must be negative in order to get that middle term to cancel. And let's actually check that so you can see what we're talking about. So here, when you multiply 5x times negative 8, you get negative 40x. And when you multiply positive 8 times positive 5x, you get positive 40x. And that's why your middle term ends up canceling here. So when you're factoring a difference of squares, the binomials are almost exactly the same. The terms are identical, but the signs are opposites in order for us to get that middle term to cancel. One has to be positive, the other has to be negative in order for the middle term to cancel. Okay, looking at number 2. So if we take a look, we have 8x squared minus 72. Neither one of these are perfect squares on their own, but if you notice, both 8 and 72 are divisible by 8. So the first thing we're going to do is factor out that GCF. So I'm going to have 8 on the outside. What I'm left with in the inside would be x squared minus 9. Oops. And then by factoring out that GCF, I'm able to see my difference of squares. I have my perfect square minus my other perfect square, and now I can factor that further. The 8 needs to be included in your answer because it's part of the factors. I'm going to set up my binomials. X times x is x squared. 3 times 3 is 9. One's positive, one's negative. And again, you could check this. You would end up getting negative 3x, positive 3x, and that's why we don't have a middle term. So this ends up being our answer here. Let me just go back in and box that one too. Okay. Now, if you look at number 3, I can see that 4 and 121 are both perfect squares, and then x squared and y squared are both perfect squares. So this one's just going to have two variables, but the pattern's the same. There's no GCF, so I'm going to go ahead and break it into my binomials. I know 2x times 2x gives me 4x squared, and I know 11y times 11y gives me 121y squared. In order for my middle term to cancel, I need one positive, one negative, and then I'm done. You can always go back and double check. We can check these mentally, like I'll say it out loud, but I won't necessarily write it. 2x times negative 11y is negative 22x. 11y times 2x is positive 22x. Negative 22x and positive 22x, they cancel. Okay, so let's look at number 4. So if you notice, 7x to the third and 2x are not perfect squares. So I'm seeing that chances are I do not have a difference of squares going on here. If that's the case, then you're just going to factor out the GCF if you can. So I'm seeing that this has x to the third, and this has just x. So I can pull out an x, I can factor that out, and I would be left with 7x squared minus 2. And at this point, I'm done. This is not a perfect square, neither is this. I can't factor this leftover binomial, this term or this expression in my parentheses. I can't factor that any further, so that's how I know I'm done. This is just a traditional factoring binomials where you would only factor out the GCF. Okay, if we look at number 5, again, I can't really tell that those are perfect squares, right? I know 7's not a perfect square, and I know 35's not a perfect square. However, they are both divisible by 7. So I can pull out that GCF of 7, and then I'm left with x squared minus 5. And now I want to ask myself what I can do going forward. So if you notice, this x squared is a perfect square, but 5 is not a perfect square. And remember, it has to be a perfect square. Straighten that out for you a little bit. It has to be a perfect square minus a perfect square. So even though x squared, right, that's a perfect square, but 5 is not, we actually can't factor this any further. We only were able to pull out the GCF. In that situation, we're done. Number 6 is kind of interesting. There's 2 different ways that we can do this. So some students might realize right away that 4x squared and 16 are both perfect squares. So keeping with that idea, right, if you just kind of jump into this without looking for a GCF first, you could factor this into 2x times 2x and 4 and 4. One's positive, one's negative, right? Because the square root of 4x squared is 2x, the square root of 16 is 4. However, if you notice, both binomials that we're left with have a GCF of 2. So we can pull out a GCF of 2, and we will get x plus 2. Oops, excuse me, let me get my eraser. This one also has a GCF of 2, so I could pull that out and be left with x plus 2. And then, if I multiply my GCFs, I get an overall GCF of 4 times the quantity of x plus 2 and x minus 2. So that's what happens if both of your terms are perfect squares and you don't look for a GCF first. It actually makes more work for you because then you have to factor out the GCF of each individual binomial. So the best way of doing this is first identifying the GCF. So here we're seeing that 4x squared and 16 both have 4 in common. So if we pull that out, notice how that gets us our GCF right away. We're left with x squared minus 4. X squared is a perfect square, 4 is a perfect square. Break it into our binomials. X times x is x squared. 2 times 2 is 4. 1's plus, 1's minus. So it really is helpful. It will save you some steps. If you factor out that GCF first, you'll get that overall GCF, because a lot of students will forget over here to factor out the GCF, or even forget to do it to both and then combine it by multiplying it. So you always want to look for your GCF first, and that's with any kind of factoring, whether you're factoring a binomial, a trinomial, or a polynomial with many terms. The first thing you should always be checking for is that GCF. Now, if we look at this one, our last one here, number 7, you know, a lot of students see the a squared and the 36, and they automatically start creating their binomials. But the problem here is that we're adding, right? And if you think about it, in order for the middle term to cancel, so let's hypothetically, right, let's kind of mess around with this. In order for the middle term to cancel, these two signs have to be different, right? That's the only way that you're going to get negative 6a and positive 6a and that middle term to cancel. So if the middle term has to cancel, then the signs have to be opposites. And if the signs have to be opposite, then this can only be negative 36. And since this is positive, we actually can't factor this. It is prime. Again, to recap, the reason why we can't factor that is the signs have to be different in order for the middle term to cancel. And if you have opposite signs, a positive times a negative will always give you a negative in the middle. If this is a positive in the middle, sometimes you'll hear of it as like a sum of squares. There's no such thing. We can't factor that. There's no GCF, therefore it's prime. Some students like to write not factorable. That means the same thing as prime. So I'll list both for you guys. Okay, and there you have it. That is our last lesson on factoring. We will continue practicing, and we're looking at an assessment in the near future, and we'll, let you guys know. But if you have any questions, reach out to your algebra teacher. You can email us. You can message us on Google Hangouts, or we can set up a time to do Google Meet as well. I hope you guys have a great day.